Okay, so we have to show this equality, which we call star, star, star. Okay. Now, why do we expect this to hold? Observe that the left-hand side, the right-hand side here is a sum of n of t minus s many IID Bernoulli random variables. Whereas the left-hand side is again a sum of nt minus ns many IID Bernoulli random variables. And moreover, all the Bernoulli random variables are independent of both nt minus s and nt minus ns. And this nt minus s and n of t minus s, n of t minus s and nt minus ns, are equal in distribution. So therefore, we expect that this equality should hold. So once again, this is a sum of ij's, j running from 1 to n of t minus s. So n of t minus s many IID Bernoulli random variables. And here, this is a sum of nt minus ns many IID Bernoulli random variables. And nt minus ns is equal in distribution with n of t minus s. And also, all the ij's are independent of both of these random variables. So therefore, we expect that this equality will hold. Of course, this is not a proof. This is just the idea why it should hold. And we will show this exactly by formalizing this idea with the help of conditioning. So let's proceed. So let's start. So this is going to be a long proof. So we are going to go rather slowly. So let's start with the left-hand side, which is the sum of ij's starting from ns plus 1 to nt equal to k. Now, of course, the problem is that both ns and nt are random variables. So it's better that we condition on ns and nt and use the law of total probability. Okay? So that's exactly what is done here. So we condition of ns being equal to m and nt being equal to n, and then multiply by the probability to uncondition it and then take the sum. Now, of course, ns is less than or equal to nt. Therefore, the joint range of ns and mt would be set of all integers, set of all non-negative integers m and n such that n is bigger than or equal to m. That is precisely what we have taken the sum over. Okay? M is running over all non-negative integers, and then n is only starting from m. That's because nt is bigger than or equal to ns. Okay, now that we know ns is equal to m and nt is equal to n, this sum here, which was a random sum, is not a random sum anymore because ns is equal to m. So this will run from m plus 1 to n. Okay, for each summand here. Now you will use the fact that these ij's are completely independent of the process. In particular, all the ij's are independent of the random vector nt comma ns. So therefore, this conditioning will go away. So we'll have this unconditional probability multiplied by this probability, and then we'll take this sum. Okay, so we have got up to this far. So we have expressed the left-hand side of star star as this probability here. Now note that we always do this, right? So the joint distribution of ns and nt is harder to find. So therefore, because they're not even independent, so therefore we just write it as probability about ns and nt minus ns. So we have done this quite a few times in this course so far. So we are going to do the same here. So instead of writing ns equal to m and nt equal to n, we are going to write ns is equal to m and nt minus ns is equal to n minus m. And these two events are the same, and therefore the probabilities are the same as well for each summand, and therefore both the sums are equal. Now, of course, we can encash the fact that ns and nt minus ns are independent, because nt is a homogeneous Poisson process, and hence it has independent increments. So let's use that. So using this, we get that this is equal to, this probability becomes product of these two marginal probabilities, and therefore this entire sum becomes this. So what we have got here is the left-hand side of star star can be expressed as this here.